Hello, everyone. My name is Ajay Jacob. I am the Director for Projects at the California Dreams Hub. Today, I have the pleasure of introducing Professor Priya Panda. She's an associate professor at the ECE at the Viterbi School of Engineering at USC. She was an assistant professor at Yale University, and she moved this year. She has been a visiting faculty researcher at Google DeepMind, and she received her BS/MS from BITS Pilani and her PhD from Purdue. During her PhD, she interned in Intel Labs, where she developed large-scale spiking neural network algorithms for benchmarking the Lohi chip. She has received several awards: Amazon Research Award, Google Research Award, DARPA Riser Award, NSF Career Award, DARPA Young Faculty Award, quite a number of awards. And it's my pleasure to welcome Professor Priya Panda, and she's going to give us a talk on systems architecture, algorithm co-design, and this is towards the energy efficient and scalable computing.
Great.
Welcome, Priya.
Thank you so much, Ajay. Thanks for having me here. I just want to give a disclaimer that I'm actually at a conference, so but I have found a very secluded room, but you might see some people moving around me, and pardon me if there is any background noise, but I hope it should not be there. So yeah, again, I'm glad to be here giving this talk to the California Dreams folks, and I'm looking forward to any collaborative opportunities that can come out after this. So in this talk, I'll be talking about the work that we have been doing in our lab on system architecture, algorithm co-design. And the way we have looked at co-design is we have looked into initially neuromorphic computing related applications where we have taken inspiration from the brain and biology to build scalable and efficient AI. And slowly, all those learnings, we have now tried to adapt it to standard ML techniques that can allow us to build these edge LLM workloads or VLM workloads in a scalable yet efficient manner. So, the need for efficient AI arises from the fact that today we are surrounded by these scaling laws. And what do these scaling laws tell us? That bigger the models become, the better they are in terms of output quality. And here is a figure that shows how the models have grown since the birth of transformers, especially around 2018, over the years, right? And you see that after the birth of transformers, the growth has been exponential. Like the models have been growing at a rate of almost 400x every 2 years. On the other hand, during the convolutional network era, which looks like a long time ago now, the models were growing at an okayish rate of 10x every 2 years. But if you compare that to your current DRAM memory, the DRAM memory is still growing at Moore's law trend, which is 2x every 2 years, right? So Gordon Moore, in his famous keynote speech, had mentioned that no exponential can continue forever, but forever can be delayed. But delaying an exponential scaling of this unprecedented rate is not going to be any more feasible with standalone hardware optimization. We really need to start rethinking algorithms, rethinking hardware, and start bringing in co-design into the approaches. Now, the thing is that given this memory problem, the fact that compute has been growing roughly like at 3x every 2 years, if you see every time NVIDIA or the new generation of architectures are proposed, there's always a compute increase. But the memory bandwidth or the interconnect bandwidth still is not growing at the same rate as that of the compute. The communication bottleneck of moving data between accelerators is even slower and even lesser efficient than on-chip data movement. And even though you try to scale out to multiple accelerators to avoid the limited bandwidth from single hardware, it will still be bottlenecked by the fact that your chip-to-chip communication bottleneck will still be there. And to break this memory wall, as I mentioned earlier, we need to start rethinking algorithms and leveraging hardware software co-design, and that has been the center focus of the research in my lab. So the first part of this talk, I want to focus on these bio-inspired models, which are spiking neural networks. Now, I was very interested in spiking neural networks primarily because of two reasons. One is that they do allow us to address the scalability challenge in a very nuanced and an interesting manner. As I have shown that, today models have been growing at unprecedented rates, and spiking neural networks, because of the way in which these models are built, taking inspiration from the brain, where you are trying to use event-driven sparse computation and communication, it really allows you to build scalable architectures with very limited power budgets. And this is again, the power budget that the brain operates at is roughly 20 to 30 watts. So that is like, if I may say so, the holy grail, where we want to build scalable, large-scale spiking neural networks for all kinds of applications that exist today, but with very limited power budgets. And why we want to use spiking neural networks and not any other bio-inspired architecture or brain-inspired model out there is because spiking models allow you to actually approach large-scale applications, right? So scalability is possible with this form of models. So in fact, today, like, back in the days, pre-2022, pre-transformer era, a lot of models were being developed for convolutional architectures, for recurrent architectures. And if you see, like, we were trying to kind of, these are some of the works from our group itself, on vision applications, especially, we were trying to bridge the accuracy gap between that of spiking models and that of the state-of-the-art models that existed from the standard artificial neural network perspective. But as soon as transformers came, what we are seeing is that with spiking transformer architectures are actually able to close this gap even further. So there is a lot of perspective in bringing attention to spiking, and there's not only an efficiency perspective there, but there is a capability perspective that we can also improve. So there is a lot of interest in thinking about large model applications using spiking transformer architectures. And when I'm trying to talk about large model applications, I'm not just limiting myself to vision tasks. I'm also trying to think about natural language processing. And this is just to give you an overview of where the field is today. So today, like, people have come up with spiking version of GPT models, spiking version of language processing models, or llama models, which are open source. And if you see, so generally, all the scores that I'm measuring are perplexity scores on Wikitext data. So lower the perplexity, better is the quality of the model. So we are seeing that in general, the spiking models have started performing at par or even sometimes better than their non-spiking counterparts. Now, there is still a lot of work happening in terms of scaling up these models from 13 billion to even larger, or trying to see, do we even need to scale to that billion parameter level, or can we get the same type of output quality at at much more higher parameter efficiency? But what I want to kind of focus my talk on today is the whole idea of using spiking neural networks was that we want to be scalable in terms of the applicability, but we also want to be energy efficient, right? And it turns out the question that one needs to ask when we deploy these models is that are SNNs truly energy efficient? Now, this is a chart that I have taken. We actually wrote a position paper in ICASP in 2024, and we took some of our works, including a lot of prior works, state-of-the-art works, that were quoting energy efficiency. And each of these works had different type of contributions in terms of training, in terms of inference, optimization, etc. But all of them were quoting these energy efficiency improvements roughly of the order of 10 to 80x, right? But if you look at how they estimated their energy efficiency, there is a little bit of obfuscated calculations here. So the way they are calculating energy efficiency is taking the flop count into effect, so number of ops, times because these models will have inherent sparsity in them. So we are looking at, like, we're taking into account the amount of sparsity that these models offer. And then one criteria of spiking neural networks that is very important is that you have to process information over time. So you have to, any information that is present, you have to process it in chunks in time period. So the number of time steps that you have to process this data for is also taken into account. That adds to the overall latency of the inference. But overall, that will be used to estimate the total energy of this spiky neural network system. Now, even though this is a reasonable enough estimated metric, but if you see, there's a lot of missing system level behaviors here, right? And the missing system level behaviors were there in these prior works because when there was no benchmarking tool available that can actually give you an end-to-end integrated and comprehensive analysis for mapping spiky neural networks on different types of hardware substrates and give you like, energy, area, latency, and performance results. So as a result of that, one of the key contributions from our group were to build hardware substrates and do benchmarking of spiking neural networks on those substrates. So we built a platform called SETA. This is a 32 nanometer CMOS based hardware evaluation platform based on a tiled systolic array architecture. And this was primarily for benchmarking SNN inference algorithms. Then we also built something called SpikeSim, and this was again a hardware evaluation platform for benchmarking SNN inference, but this was based on a compute in memory architecture. So it primarily was supporting RAM devices with network on chip communication. Then, very recently, we also have started building sparse accelerators. I mean, where the weight sparsity and the activation sparsity of spiking neural networks can be combined for accelerating and benchmarking inference with spiking neural networks and trying to see if they will be able to give us better benefits than, let's say, sparse accelerators that are being proposed for standard ANNs. So I will try to give you some benchmarking study analysis from each of these works. But first and foremost, what SETA, the first work, the systolic array work told us was that there is a lot of data movement that is involved. And in this estimation of energy that we are doing, no data movement, no data flow or memory related costs is getting accounted for. So we really need to start bringing in data movement into the picture. And turns out that when I say data movement, it is not just the weights that occupy a large fraction of your data movement, but it can be also the membrane potential. So membrane potential can be thought of as intermediate activations for a spiking neural network. And it turns out that they also carry a lot of, meaning they are also responsible for this overall data access and fetches and latency. And in fact, depending upon the type of model you're working with and the resolution of the data you're working with, it might be possible that the weight is to membrane potential ratio in terms of data movement can switch. So for a smaller resolution data, you will have more weights accounting for data movement, whereas for a higher resolution data, you will have more membrane potentials, which are the intermediate activations that are accounting the majority of the data movement. So basically, the key takeaway was that, the expensive DRAM and buffer accesses for both weight and membrane potential dominate the total energy cost. And it turns out that this total energy cost that is dominated by memory keeps on exacerbating as you increase the number of time steps that you have to process the input. As I said again, spiking neural networks process information over time. So this time step information is there. So as and when the number of time steps increases, you will also start seeing more and more increase in terms of the total energy cost. So the question then becomes that how do we mitigate data movement, right? So we actually looked at some standard compression techniques to mitigate data movement. And these are like, algorithmic techniques that were finally, eventually, could bleed into hardware benefits. So we looked into quantization, for example. We have looked into pruning algorithms. In fact, not only pruning, but also sharing of information between layers because spiking networks have inherent temporal dynamism in them. So across time, you can share information. So that could give you some reuse opportunities and can alleviate some data movement related overheads. And then finally, we were also trying to look into if the everything exacerbates with time, then can we reduce the number of time steps required for getting quality inference from the data? And we did some work there. So of course, I will not have time to go over each of these methodologies, but I'm going to be just focusing on the quantization work that we published last year. So in the quantization work, if you see, the idea is to quantize both the weights and the membrane potential. So that is the first idea, that you cannot just quantize only the weights. you have to quantize the membrane potential as well because they also account for a large fraction of the memory movement. Now, when we are quantizing the weights and the membrane potentials, it turns out, as you may have, some of you may have know, that in quantization, generally scaling factors are introduced in order to make sure that post quantization, when you do the calibration, if you don't bring in scaling factors, then your output accuracy is going to take a hit. Only with scaling factors, your output accuracy is not going to take a hit. But the problem is that when you bring in scaling factors, again, you have to reintroduce very complicated circuits, meaning a multiplier circuit has to be brought in. Maybe the scaling factors can be of float precision sometimes and not of really low precision. So it brings in a lot of unnecessary system overheads in terms of area, in terms of energy. So what we wanted to do was that we wanted to take advantage of the computational dynamics of a spiking neural network and see, can we get rid of these scaling factors that introduce in unnecessary system overheads on a quantized framework. So what we decided was that we will share the scaling factors, right, that are introduced, and these scaling factors later on can be folded into the computational activation mechanism of a spiking neural network, which is called the thresholding mechanism. I'm not going to go into the details of that, but it turns out that threshold is a hyperparameter, and this scaling factor is also a hyperparameter that you can determine during calibration. But it turns out that because of the way in which the spiking neural activation function works, so we can have this shared quantization across different layers of the spiking neural network, across its convolutional layer, across its activation layer, and then fold the scaling factor directly into this hyperparameter called threshold. And as a result of that, we get an end-to-end quantization framework where the scaling factors are no longer required. So you will have low storage of weights, low storage of potentials, and actually you don't need any multipliers as such just because of the introduction of scaling factors. So going to quickly the results, we found out that this approach, we called it multiplier less integer quantization for spiking networks. So the name MINT was an acronym we used. So with MINT, we were able to see that we are going up to 2-bit weight and 2-bit membrane potential quantization. And this is all integer 2. So we are going from float 32 to integer 8, integer 4, and integer 2. And you see across all of these models, we get up to 93 to 94% total memory footprint reduction. And then in terms of accuracy also, as compared to that of the original FP32 model, across different architectures and data sets, our accuracy with a 2-bit weight and 2-bit activation was maintained. And then finally, we also found that, like, total energy, because of the fact that you're using now a quantized framework. So because of the 2-bit quantization, the amount of data movement energy reduction is around 80 to 85%. And that again translates to the total energy and total computation energy cost reduction. So that was one aspect in which we were able to reduce the total, in some way, energy by focusing very much on the data movement related cost that this particular estimation did not account for. Now, the next thing that is obfuscated in this estimated metric is that the sparsity that is considered here is unary sparsity, meaning that when all the algorithmic people consider that, okay, there is a sparsity, meaning what, there is a zero coming in my model, meaning that I'm not doing any computation for that zero, right? They assume that there's no computation being done for that zero, no fetching, no computation, nothing. But that is not true actually, right? At an architecture or a system level. So as I will show you that fully leveraging unary spike sparsity is actually challenging. And why is that so? Let me show you with an illustration. It will make things clear. So with a spiking neural network, the output of the network looks something like this. It's kind of going to be this sparse matrix that you get of ones and zeros, okay, across different time steps. As I said again, you process information over time. So time is always a part of your output dimension. But essentially, you will get this kind of a sparse spike matrix. Wherever you see a yellow, that's a one. And wherever there is no yellow box present, these are all zero. So you'll get this one and zero matrix. So this is how it's going to look like, let's say, right? Now, interestingly enough, if you see here, um, if let's say the spike train, the input spike train looks something like this, 0, 0, 1, 1, right? Now, what I can say is that, okay, I might be able to use some gating in order to reduce my number of computations, meaning I will only compute when there is a 1 and not compute when there is a 0. But that doesn't mean that the number of cycles I have to process my processing engine for is reducing. I have to still process my processing engine for 6 cycles, which is the total number of cycles, which is the total number of time steps that I have to process the spike train, right? So the sparse spikes can help reduce computations, but not the overall latency. That's the first thing. The second thing is that now you can tell me that, you know what, I'm going to now, like, not even bring this entire spike train with zeros and ones. I'm going to skip the fetch of the zero spike such that I can start saving the PE cycles. And how can I do that? If I can store my spikes in some compressed format. So let's say that's the same spike train. If I want to store it in a compressed format, I have to store its non-zero values, right? And some indices, right? Which will tell me where the non-zero values are present. Now, as a result of that, I can now have number of cycles also reduced. But in this case, as an example, I'm just telling you that in order to compress just 3 bits of data, you need three 3-bit indices. Okay. So that is going to give you a very low compression efficiency of less than 1, right? And this is generally going to be the case for you. So unary spike sparsity exploitation is very, very atypical and difficult. So what we decided was that instead of leveraging unary spike sparsity, let's start leveraging what we call a silent neuron sparsity. So in your spike matrix, you will actually have some rows where all neurons will never spike, right? So if you see this row here, this neuron has never spiked across any time step. Similarly, this neuron here, the second neuron, third row neuron here, has never spiked across all time steps. So these are the neurons that will be referred to as temporal or sorry silent neurons. And what we can do is when we try to do the compression, we will try to compress along the temporal dimension such that we can take advantage of silent neuron compression. So this is what we will do. We will start packing our compressed spikes along the temporal dimension, and as a result of that, we are essentially now storing this information using a bit mask pointer value. But the idea is that you will only store the non-silent neurons and the bit mask and the pointer corresponding to those non-silent neurons, and this will give you an overall compression efficiency which is going to be more than 1, right? And it turns out that why can we take advantage of the silent neuron across a lot of workloads, from CNNs, in vision problems to transformers in language processing models. We have seen that spiking models generally exhibit up to 79 to 85% of silent neuron sparsity. So there is a lot of compression efficiency to leverage if you can do this kind of packing along the temporal dimension. So we decided to go ahead and do that. But on top of that, on top of this kind of packing, we also wanted to come up with an architecture or a system level evaluation that allows us to also get around the sequential processing of information that happens in a time step wise manner in a spiking neural network. So to get around the sequential processing of information across time, we went ahead and modified the data flow that we have to use in the model. So it turns out, like, if you look at a data flow today, generally the data flow will have some for loops, and each for loop, let's say M and K is a standard data flow that does matmul, right? So the M and K are the weight matrix and the input matrix dimensions, right? Now, when you introduce a time step in that into the flow, so now there will be a for loop corresponding to the time step because that gem M and K operation will happen for each and every time step. But that means that now you are increasing that the number of workloads are increasing because of the for loop that is introduced because of this T time step. So what we decided was we tried to come up with a temporal parallel data flow where we put T as the innermost true loop and then start spatially unrolling it. So this is called as like a fully temporal parallel data flow. Again, in the interest of time, I'm going to be a little bit more brief in my discussion, but happy to discuss this later at the end of the presentation. But now what happens is, as a result of that, the gem operation itself has become independent from the number of time steps. So there is not like the sequential processing overhead that is happening because of time steps on the gem flow. So combining these two things, which is this efficient spike compression because of silent neuron sparsity and this fully temporal parallel data flow, we proposed what we call as a dual sparse SNN accelerator called LUAS. And here dual sparse means the activations are anyway sparse in a spiking neural network because the activity, the spike activity is what you have as a sparse output. And now we have also introduced weight sparsity, meaning we're doing some unstructured pruning of weights. And then we introduce this end-to-end SNN accelerator. And quickly going over the results, we found out that because of the data flow and the compression, we see that LUAS has almost 5x lower data traffic as compared to prior works that were also trying to take advantage of some dual sparsity in SNNs. They came up with their own way of managing the sparsity. And in terms of energy efficiency, we found that LUAS yields 2.4x better energy efficiency or nearly 45x speed up as compared to prior dense SNN accelerators. Dense SNN meaning the activations are sparse, but the weights are dense, right? So because of now that we are taking advantage of the weight sparsity also, so that's where the primary speed up is coming from. So now to do an apple to apple comparison where let's say we are running a ANN, meaning a normal network with ReLU neurons with maybe the weights are still sparse, so a dual sparse ANN and a dual sparse SNN comparison. It's the same VGG16 architecture that we ran for both of them. And both SNNs and ANNs will have 8-bit weights. We found out that now the energy efficiency comparison between an ANN and an SNN in this apple to apple manner is the energy efficiency of an SNN is just 1.9x more, right? And this energy efficiency primarily comes from two reasons. One is the fact that we have this silent neuron sparsity, which is much, much higher in case of a spiking neuron, almost 79%, versus the general sparsity that is observed with a ReLU-based neuron that is around 40 to 50%. And then, of course, the activation uh, bit footprint of a spiking network is going to be lower. It's going to be overall 4 bits, whereas in case of an ANN, because of the dense activations, it's going to be 8 bits. So these are the two reasons. But now this is going to tell you, like, so from all those 20x and 10x numbers, now we have moved to 2x. And this is what true benchmarking allows you to do. It tells you, like, where are the bottlenecks and what can you do and where can the speed up lie and what and whether those numbers are correct or not. So moving on, so from sparsity and from CMOS based engines, we also started thinking about benchmarking on compute in memory engines. And the compute in memory engines, the idea was that we wanted to use now crossbars. I think the audience here might be very familiar with crossbars. It allows you a very high throughput matrix vector multiplication where you feed in the inputs as voltages to the rows of the crossbar. And at the cross point of each crossbar can is sitting some kind of a device like a memristive device, and then these voltages interact with the conductance to give you some current. And then at the when you measure the current at the column of the crossbar, it's actually going to be this weighted summation or dot product operation that you're expecting from a standard a GEMV operation here. So the reason why we wanted to start thinking about putting SNNs on in-memory computing is there are a few advantages to it actually. So it was not just trying to benchmark SNN on a new hardware substrate, but there was an advantage to it. So firstly, the first advantage was that in a crossbar, if you have a crossbar architecture, you want to activate as many rows as possible. That means you want to have highest throughput, right? So high row parallelism is preferred. And since in a spiking neural network, the inputs are going to be binary and very, very sparse, you can actually have a higher row parallelism here. And the second thing is that because of the, again, the sparsity in the input and the output, the peripherals are going to be much, much simpler, meaning that, for example, the ADC that would be required at the column periphery of the crossbar is going to be of lower precision. Similarly, for the weights, we don't need very high level integration and accumulation circuits, we can get very simple shift and add only for weights. So using having these advantages in mind, we designed integrated circuit to algorithm benchmarking frameworks for spiking neural networks for in-memory computing substrate called SpikeSim. And SpikeSim was essentially a tiled array architecture here. As you can see, that there are multiple tiles connected using an NOC. Each tile comprises of multiple processing engines connected using H tree. Then each processing engine comprises of multiple crossbars, again connected using H tree, and each crossbar is this in-memory computing crossbar that you have. Now, what SpikeSim allows you to do is that once any user, right, whoever has an algorithm spiking network, it can give their they can give that algorithm checkpoint model to the SpikeSim framework. It will run its own partitioning to figure out how many crossbars, how many tiles, all of it is required for that algorithm or for that model. Then it will do a floor planning, meaning that once the user has given some parameters like crossbar size, device precision, etc., it will try to initialize the SpikeSim based on those parameters, and then finally it start proceeding to inference stage, where it will internally run two tools. One is an energy latency area analysis tool that does active layer tracking, NOC trace generation, and measures real-time energy latency area. And then it also runs a hardware realistic inference by integrating non-idealities to give you, actual accuracy, actual hardware realistic accuracy rather than estimated software accuracy. So this is a very powerful SpikeSim tool. It is again available on GitHub on our website. So those of you are interested can also use it. So first and foremost, because the whole talk is focused on some insights that we are getting when we do these benchmarking. So the first thing we wanted to we were very interested in is that are we actually getting some peripheral reduction, because that is what a lot of compute and memory researchers are interested in today, right? How to reduce peripheral circuit overhead. So the turns out that firstly, SpikeSim, we decided to use a flash ADC rather than a SAR ADC with spiking neural networks, because anyway spiking neural networks have an extra latency overhead because you have to process information over time, and we wanted to optimize latency over area that flash ADC allows you to do. So we want use flash ADC. Then the next thing we found out was that because of the binary sparse spike inputs that are present in SNNs, 4-bit ADC was sufficient enough for partial sum accumulation. Whereas in case of a standard ANN, which has, let's say, 4-bit weights and 4-bit activations, you generally need to use a 6-bit ADC, right? So because of this reduction, 2-bit precision reduction between an SNN and an ANN, we get almost 50% area reduction and nearly 60% delay reduction per crossbar with SNNs as compared to a standard ANN. So that's the first advantage. But when we did an energy and area breakdown, we still found out that even in case of an SNN, the digital peripherals, which can be buffers, ADC, H tree, NOC, all of that, they still dominate the total energy and the area cost, right? And then we also found one other thing. If you see here in the area graph, that almost 25 to 30% of the area is being utilized by a digital uh, activation module, which is the LIF module that we use for spiking neural activation function. And since we implemented it using a digital module, so an integrate and fire circuitry we have to implement. So the integration has to use some kind of accumulators. So there has to be some kind of a SRAM cache to do that accumulation. So it turns out that because of that, the area overhead of this activation module increases in case of a spiking network. Now, if you compare that to that of a ReLU activation that an ANN uses, which is just a simple comparator operation, so you see that in terms of just an area comparison between a digital LIF module and a digital ReLU module, you see there is almost 1000x increase in area requirement for storing this LIF module in a digital manner. So there has to be something we need to do in order to reduce this area overhead. So what we decided was that given that the area overhead is huge, can we do some, again, architecture redesign or algorithmic changes in order to meet the constraints of the hardware? So this is again the co-design technique. And the simple thing we started to look into was that can we modify the architecture of the model? And by modifying the architecture of the model, we meant that we are reducing the total number of channels or the total number of hidden dimension that would be required in the model. And we found out that when you reduce the number of channels, overall, we found that there was a decrease in terms of the neuronal area overhead that was required. So almost 2x lower LIF or IF module area was achieved, and that resulted in 25 to 20 at 25% reduction in energy and 14% reduction in latency. So overall, there is a benefit in terms of digital periphery reduction, but there is an extra overhead because of the LIF area. So you need to come to terms with, whether these benefits in general will outweigh some of the overheads cost that you have. So in this case, just to put everything together, this slide here measures or compares the peak performance, which is measured in GOPS per second versus power across different accelerators for both ANN and SNN. So all the green points you see here are all ANN accelerators that have been pushed, that have been all benchmarked on prior digital modules. Then the blue point that you see here is theta with an SNN. The red points that you see here is again SNN on an IMC hardware substrate like SpikeSim. And then the yellow points that see here are the ANNs on an IMC substrate. And ANN meaning I'm just using a standard ReLU based architecture. Okay. That's what I'm referring to as an ANN. So what you see first is, in general, whenever you have a spiking neural network substrate, the power is lower, maybe at the same performance. But when we bring in IMC substrate there, at near ISO performance, the power further reduces, right? And then if we bring in LOAS was that dual sparse accelerator that we talked about. So this would be compared with something like SETA, which is a dense accelerator. So here we found out that at near ISO power, we get a 50x speed up in performance just because of the sparsity acceleration we are able to achieve. So this overall picture hopefully tells you like where can SNNs fit and where they are not a good fit. But to summarize, why would you use SNNs and where would they be a good fit? Well, energy efficiency is the primary advantage at this point, especially, and they are very, very relevant for edge computing, robotics, and autonomous systems. Um, and one thing I want to also say is that today, don't think about building spiking neural networks from scratch. They should be treated as a feature rather than as a backbone today. Okay. That means that you can be using spiking as a booster to already existing hierarchies. Then finally, like when you are thinking about energy efficiency with spiking, make sure you benchmark them on actual hardware such that you know what type of sparsity advantages you're taking care of. The final thing I also want to talk about is that besides neuromorphic hardware-centric solutions or ASIC solutions, it is also important to build general purpose hardware efficient spiking algorithms like we did with this quantization algorithm called MILT. Because that way you can propagate spike-based AI into multiple applications, right? And for that, you really need to start thinking about having some kind of a software support that can eventually accelerate spiking models, especially during training. Right, so some QPy and GPU support to train SNNs faster, and then bring this kind of hybrid format faster would be also very, very relevant as we are building large scale models with them. So in general, this is a good segue to what I'm doing next. From biologically inspired, scalable, efficient models to general efficient scalable models is something that we've been also looking into. So if you see, the summary of the work that we have done in the past, we have built a lot of algorithms and hardware tools primarily focused on spiking networks, but the learning from here has helped us now develop systematic design space exploration and optimization tools for efficient AI. So I have like another 10-15 minutes. So in the last 10-15 minutes, I'm going to be actually giving you an overview of one or two works that we have done in this design space exploration works. And then if you see that most of these design space exploration works will be primarily for edge AI applications where you are trying to build more real-time, adaptive, and automotive solutions. So in efficient AI, if you think about any time when you're thinking about building efficient AI in and hardware software co-design, so there's a lot of design considerations that an architect or a person needs to think for building the right kind of accelerator and the right kind of hardware, right? So given a model, you need to see the type of hardware resources your accelerator has, then you decide the mapping, and the mapping is going to be like, okay, what type of tiling I use, what type of ordering, what type of parallelism, the type of shape I will use. This is all coming under data flow. Furthermore, the model will have different design parameters to choose from. What is the size of the model? What is the precision? What is the sparsity? Again, in terms of hardware resources, you have to decide number of P's, size of the buffer. Am I going to do voltage scaling or not? What type of switch connect I will use? If you're building an in-memory computing substrate, the design choice further explodes, right? So all of these choices will finally determine what's your power, energy, latency, area, accuracy trade-off, right? So if you see, there's a huge interdependent design space between algorithms, compiler, which is going to determine your overall data flow, and the system parameters, whether it is for a compute and memory substrate or a CMOS historic array-based substrate, right? So what we need to start thinking about is coming up with a framework that allows you to do some kind of network architecture, automatic discovery using some search-based algorithms. And we want to bring in not only heuristic search, but also some ML guided search, right? So what we are doing is we are following a three-step process to do the systematic design space exploration and optimization. So the first step of that process is we want to specify what the design space is and what type of hardware accelerator are we trying to optimize for. Now, specifying the design space is also important because the design space is going to be huge and it's searching in the entire space is not going to be feasible. So we want to search, we want to narrow out the scope. That's why we want to specify the design space. And then the second is based on the hardware accelerator and the design space that I want to search for, I start characterizing some of my metrics like energy, latency, area, and then maybe I can build some differentiable functions out of that characterization analysis that later on can be plugged in into my core search optimization algorithm. Whether you are using, let's say, reinforcement learning, so you can plug in this function as into your loss objective, or you're using, let's say, neural architecture search or some NAS based algorithm, right? So ultimately this joint co-optimization between algorithm design candidates and hardware parameter system parameter candidates will allow you to get a better trade-off between energy, delay, area, and accuracy constraints. So we will see a couple of works that we have done in the recent past following this three-step recipe as I talked about. The first work I want to talk about is in the framework of in-memory computing. Here we designed a framework called Expert that optimizes a couple of things. Mainly from the system perspective, it is optimizing the peripheral parameters that are there in your in-memory computing platform, like ADC type, precision of the ADC, multiplexer, meaning how many columns will you share. Also, and from a model side or the algorithm side, we are trying to optimize the network architecture itself, meaning we are trying to optimize the number of channels that each layer should have. Also, we are trying to optimize the precision of the activations of each layer. So this framework, I mean, it's a phase-wise framework. It's a big framework that we build, end-to-end framework based on PyTorch again. But the idea is that we build this framework in a phase-wise manner. So this search or optimization that we are doing is also done. I'm sorry, just give me 1 second. Yeah, sorry. I'm in a conference, so there is a little bit of noise from coming from behind, so I hope it's not too much.
We are not hearing any noise.
Okay,
Priya, go
wonderful.
ahead.
I know I just
Yeah.
moved a little bit out, so that's fine. Yeah, so basically what I'm trying to say is here that we did this phase-wise search, and in the phase-wise search, if you see in the first phase, we are trying to optimize some system parameters and some model parameters with area and delay as our main constraints given to the loss objective. And then in the second search, we are looking into the ADC precision and the input precision where we are further optimizing the delay. And in between these two searches, we have an intermediate phase where we are training the model for accuracy. Okay. And in both the searches, we are never training the model. Only in the in between, we are training the model. So these searches are actually going to be meaning hyper speed. I mean, it will take a few seconds for every layer to get you the right kind of parameter. So we kind of detach training from the search in order to make sure that there is not like an overhead in the optimization process. So coming back to again, I like to show these power performance figures to tell you like where our search based methodology and the design finally we created using our expert framework. Where does it lie as compared to prior ASIC design works? So here I'm comparing expert on INC with Neurosim. Neurosim is a very popular in-memory computing evaluation framework from Shiming Yu's group at Georgia Tech. We also compared with a few in-memory computing works that were proposed in ISSCC. And you see here that in terms of overall power and performance, we are getting 3x higher tops at 1.25x power reduction compared to the Neurosim baselines. So all these searches that we started doing, there was a framework called Expert, there was a framework called Mime that I don't have time to go over, but we were always optimizing the energy delay for static targets, meaning that I want to do the search for a given energy of, let's say, certain joules. I want to do a search for a given latency of, let's say, 1 second or something. But if you think about in real time, this is not going to be the case, right? Um, Real world scenarios require adaptive computation scaling, meaning depending upon where how your battery conditions are, you need to start scaling your compute such that you can meet latency constraints with the given battery constraint with the given battery conditions. So to do that, we started now thinking about, algorithmic co-design or algorithmic optimization in addition to system parameter optimization. So if the main idea with what we wanted to think about was that when we did do this adaptive hardware computation, can we bring in some kind of input awareness to it? Meaning in real time, whatever inference is happening, can I think of based on the type of input that my network is seeing, I'm going to scale my compute based on that. So as an example, I'm showing you two types of inputs here. Both are chairs, but I can easily say that this is a chair with less time and effort. For this one, maybe because somebody might be confused in the first go, right? Okay, this looks like eggshell, but then you will see that, oh no, they are all laid out in a meeting room or a conference room. So that means that these might be also some kind of chairs. So meaning that like, there will be a lot of such real world data out there where certain inputs can be considered as quote unquote easy and certain will be considered as quote unquote difficult. So we actually use this idea about input difficulty aware scaling in order to bring in this input aware inference in vision transformer models, where easy inputs would be classified with low effort and difficult inputs would be classified with high effort. And we started doing a benchmarking not only on in-memory computing platforms, which I will show you later in the slides, but also on standard FPGA-based frameworks. And again, we did this entire co-search and optimization, meaning that we have to figure out what is the type of effort that will give you the best combination to achieve the best accuracy for different types of delay constraints that might be present in the hardware depending upon the battery power available. And we did this kind of a co-search optimization using a neural architecture search based algorithm and optimization loss objective based formulation essentially. So to give you the quick results on what we saw on an FPGA, so we benchmarked this kind of scalable effort evaluation on a low power CCU 102 FPGA. So we found out that we are getting almost 5x reduction in energy delay product with our model, which is called as pivot, as compared to a standard model where there is no input aware effort scaling happening. And we also went ahead and benchmarked on a Raspberry Pi CPU as well as a standard Jetson or in Nano. And we found out that our input aware adaptive scaling also worked there, where we got 1.8x lower end-to-end delay. Delay meaning per inference latency. We were able to even reduce that by almost 1.8x on edge GPUs and microcontrollers. So this was a very effective technique. Um, this is just telling you some qualitative results when because we were working on vision data. So we found out that what the model qualifies as easy versus what the model qualifies as difficult is actually very intuitive. Let's say for oranges, wherever the image is present as a whole, it qualifies as that easy. Wherever the image is present in terms of multitude, it qualifies as that difficult, right? Now, next, what we went ahead and did, and this is the last slide, meaning last topic I will discuss before I end, is that we wanted to take this idea about this scaling of effort based on input awareness and try to push it towards the in-memory computing based platform. Now, the thing is that with in-memory computing, with CNNs, it's very easy. Why? Because the entire CNNs are all static in terms of post training the weights are static. So it's a weight stationary architecture that matches the in-memory computing substrate very well. But if you try to think about matching an attention or a transformer block into a in-memory computing substrate, then what happens is that there are some matrices, there are some operations, especially the QK transpose or a softmax V operation that would require you to continuously keeping on writing your K and V values in your crossbars that are storing these matrices. Okay, so there are some dynamic write operations, and that will contribute a lot of portion to your overall delay because writing into a non-volatile memory crossbar is going to be very, very difficult. So we find that generally in an in-memory computing substrate, attention contributes 75% of the delay. Out of that 75%, K and V write operations contribute almost 50% of the delay. So what we decided was that we should now think about having a hybrid crossbar architecture where we have read-only crossbars for certain static layers in your model, and we have some more efficient crossbars for doing the dynamic write operations. So we decided that we will use an SRAM for your write crossbars, and we will use a FEFET which has low area and variations for your read-only crossbars. Now, based on that, once we decided we will go ahead and build this in-memory computing hybrid architecture, hybrid device architecture, we went ahead and deployed our attention skipping algorithm on these IMC substrates. And what we found out, firstly, is that this was your earlier pivot across a Raspberry Pi, NVIDIA Jetson, and ZCU 102, which was doing attention skipping based on input awareness. And now when we brought it to a in-memory computing substrate, we find that at almost 1000x lower power, we are able to increase the throughput by 15x. And furthermore, as soon as we brought in this hybrid IMC with FEFET and SRAM both, SRAM for write and FEFET for read only, we were able to further improve the throughput by 1.22x at 4x lower power. We also kind of, did these analysis on large language models, did the input aware skipping on crossbars using large language models. We got overall tops per watt improvement as well as tops per area improvement. So I'm going to skip these slides in the interest of time. We went ahead and also implemented the same in the interest of time. I'm just going to skip this slides, but in collaboration with IBM Research, we went ahead and implemented in addition to attention skipping, some improved data flow and compression strategies for pushing large language models on low power FPGAs. And there again, we found out that wherever these FPGAs do not have, they have very limited bandwidth, this attention skipping with the right kind of data flow and memory compression strategy can still give you end-to-end latency benefits of around 1.5x. And these were all demonstrated on OPT models of 125 million and 1.3 billion. And this is an end-to-end implementation on, again, Xilinx is ACU 102 FPGA. So overall, there's a lot of now we have started looking into edge LLM acceleration works, which look into quantization, model compression, in addition to the design space optimization that I've been talking about. Similarly, activation sparsity and sparse acceleration, fine tuning. How can you do fine tuning and combine it with design space optimization and design space core search is something that we have also started looking into. So finally, what I want to give you as a key takeaway is that there is a need for cross-layer innovation at architecture, system and data flow to cater to the dynamically varying constraints, especially for these language model and vision language model workloads. We are seeing that maximal speed up gains are possible by integrating cross-layer techniques with hardware awareness. And today, at least, like I know a lot of work, or my work has also focused on inference, but we are slowly starting to move into fine tuning, and fine tuning efficiently is of great value to the end user. So optimization techniques, both in this core search manner, need to be also fine tuning friendly. So yeah, this is a final takeaway slide in terms of end-to-end code design and optimization will pave the way for next generation of ubiquitous computing, where hardware will drive software design and software is going to be driving hardware design. So yeah, thank you all for having me. And again, I'm sorry if there was some noise at the background, but thanks to all the sponsors and my students who have made this work possible.
Thank you so much, Priya. It was a great presentation. Quite a lot of information here. I mean, a lot of spike neural network calculations and a lot of code designs involved. But is there any questions for Priya? It seems if there are any questions, please raise your hand and you can come to mic. Okay. It seems there are no questions. So I have one question for you, Priya. You discussed about biological intelligence as well as the artificial intelligence. So when it comes to these two, how do you differentiate, or which one is more important? Is it the bottleneck? Is it coming from the algorithm, or is it coming from the memory movement?
Yeah.
Or is it from some device level energy optimization that we requires to do?
Yeah, that's a good question. So I think today, for example, like biological intelligence, today the focus is on making algorithmic improvements to improve their capabilities, right? And when we started building spiking network, we went the capability route, we started scaling them up. But the problem was that suddenly we found out that they are also going through the same issues in terms of data movement bottlenecks, and there are issues in terms of if you don't manage the data flow, there will be a lot of and if you don't manage the sparsity well, then the overheads cannot be really giving you any benefits, right? So as soon as we started thinking about capability, then system benchmarking allowed us to understand, okay, where are the bottlenecks lying? Now, on the standard efficient, like attention based things, I think the capability is there, but we know that to make them even more capable, you need to scale them up in terms of count, a parameter count or compute. You need to throw more compute at them, and there I feel the reason why we are doing that is um, yeah, attention, the way attention came up with it was it's sort of like a very brute force way of remembering things, right, rather than thinking in a context aware manner. So I feel that um, in some way bringing biology and attention together, maybe this context awareness has to be more nuanced, such that somewhere we can also take advantage of the memory hierarchy there. But having said that, coming back to the main point is that with attention, capability was always there. So then people started thinking about efficiency techniques, whereas with biology, people are just trying to bring up models to increase their capability, and then the system level benchmarking is always an afterthought. So that needs to change. It has system level benchmarking has to go hand in hand with capability improvement as well.
Thank you, Priya. It seems there are no questions. Let's discuss the next week's technical seminar. It's next week, December 12th. Andre Ferron from Caltech is going to give us the talk. And thank you all for attending this seminar, technical seminar series. And thank you, Priya, once again.
Thank you. Thank you so much. Bye-bye.
Bye-bye.